Okay. So we are going through this section, 1.7. Let's just make sure that the mic is right. It looks like it. Okay. So, okay, so where were we last time? We were sort of building up to what this section is about, which is bifurcations, by talking about equilibria and the phase line, where basically for an autonomous differential equation, we can characterize the behavior of trajectories just based on a single line along y that shows how trajectories move in between equilibria. All right, so starting with that as the background, in many of our models, a common feature is the presence of parameters along with variables. Parameters are quantities that do not depend on time, but that assume different values depending on the specifics of the application at hand. For instance, the exponential growth for population contains k, the constant of proportionality of the growth rate. One of the underlying assumptions of this model is that the growth rate is a constant multiple of the total population. However, when we apply this model to a different species, we expect to use different values for the constant of proportionality. For example, the value of k we would use for rabbits would be significantly larger than the value for humans. How the behavior of solutions changes as the parameters vary is a particularly important aspect of the study of differential equations. For some models, we must study the behavior of solutions for all parameter values in a certain range. As an example, consider a model for the motion of a bridge over time. In this case, the number of cars on the bridge may affect how the bridge reacts to wind, and a model for the motion of the bridge may contain a parameter for the total mass of the cars on the bridge. In that case, we would want to know the behavior of various solutions of the model for a variety of different values of the mass. In many models, we know only approximate values for the parameters. However, in order for the model to be useful to us, we must know the effect of slight variations in the values of the parameters on the behavior of the solutions. There may be effects that we have not included in our model that make the parameters vary in unexpected ways. That's interesting. In many complicated physical systems, the long-term effect of these intentional or unintentional adjustments in the parameters can be very dramatic. In this section, we study how solutions of a differential equation change as a parameter is varied. We study autonomous equations with one parameter. We find that a small change in the parameter usually results in only a small change in the nature of the solutions. However, occasionally a small change in the parameter can lead to a drastic change in the long-term behavior of solutions. Such a change is called a bifurcation. The way we say that a differential equation that depends on a parameter bifurcates if there's a qualitative change in the behavior of solutions as the parameter changes. Okay, so the notation for differential equations depending on a parameter. An example of an autonomous DE that depends on a parameter is y squared minus 2y plus u is equal to dy dt. Mu. The parameter is mu, the independent variable is t, and the dependent variable is y. Note. All right. What's up, Riley? Hey, how's the mic quality on this one? Is it? It's probably not that. It's probably not very good. but because it's using the old type of mic. But anyways, all right. Note that this equation really represents infinitely many different equations, one for each value of mu. We think of the value of mu as a constant in each equation, but different values of mu yield different differential equations, each with a different set of solutions. Because of their different roles in the differential equation, we use a notation that distinguishes the dependence of the right-hand side on y and mu. The parameter mu appears in the subscript, and the dependent variable is the argument. If we want to specify a particular value of mu, then we write f. Oh, I don't really like that notation, but that's fine. Okay. Yeah. I don't think this is the worst. All right. We use this notation in general. A function of the dependent variable y, which also depends on a parameter mu, is denoted by f sub mu of y. The corresponding differential equation with dependent variable y and parameter mu is, okay, great. Such a differential equation really refers to a collection of different equations, one for each value of mu. We call such an equation a one-parameter family of differential equations. Okay. One parameter family of differential equations. Okay. A one-parameter family with one bifurcation. Let's consider y squared minus 2y plus mu. For each value of mu, we have an ADE, and we can draw its phase line and analyze it using the techniques of the previous section. We begin our study of this family by studying the differential equations obtained from particular choices of mu. Since we do not yet know the most interesting values of mu, we just pick some random values. In general, mu need not be an integer. Okay, fine. For each mu, we have an ADE and its phase line. Okay, great. So if we started off with y squared minus 2y minus 2, we get these equilibrium points, and between the equilibrium points, we get f sub the function. Okay. Between the equilibrium points, dy dt is negative, and above and below, it's positive. So we have this phase line. How do you factor this? Oh, I guess you could just use the quadratic you could just use the quadratic formula. Yeah. Well, it was clipping earlier, but now it seems to be at like minus 10 dB, which is kind of where I want it. Oh, but it does seem to, yeah. I don't know. All right. Okay. Y squared minus 2y minus 2. All right, so here's a collection of phase lines. Each of the phase lines is somewhat different from the others. However, the basic description of the phase lines for -4, -2, and 0 is the same. They're exactly two equilibrium points. The smaller one is a sink and the larger one is a source. Although the exact position of these equilibrium points changes as mu increases, their relative position and type don't change. Solutions of these these equations with large initial values blow up in finite time as t increases and tend to an equilibrium point as t decreases. Yeah, the thing about it blowing up in finite time is actually really weird. Dude, I'm so tired right now. I went to lie down for a second and I just like got so tired. Okay. Solutions with very negative initial conditions tend to an equilibrium point as increases into Okay, so yeah, so here's the solution sketches. Okay. We have something very different if mu equals 2 or 4. There are no equilibrium points. All solutions tend to plus infinity as t increases and to minus infinity as t decreases. Because there is a significant change in the nature of the solutions, we say that a bifurcation has occurred somewhere between 0 and 2. Um, all right. To investigate the nature of this bifurcation, we draw the graphs of f sub mu, the u values above. Okay. Okay. Okay, here. So, right. Okay. So here's what it is. So yeah, so you get the equation that has the parameter in it, y squared minus 2y minus mu. And you set it equal to 0. Then you use the, what is it, minus b plus or minus square root of. So you use the quadratic formula or equation or whatever, and you get what? You get 2 plus or minus 4 minus 4 times 1 times minus mu. Or wait. I mean, that's interesting. It's minus mu. Oh, it's plus mu. Yeah, see, because that it doesn't really matter. Over 2a. Wait, hold on. Yeah. You got That's pretty funny. You didn't get me though. Not yet. Still kind of busy. All right, so what do we get here? We get um Okay, I got this. Took me forever though. Oh, I don't really. Yeah, I don't really game. The only game I think I've ever played on stream was Factorio. I played it with Mr. Bob Simple. All right. Okay, so we found that when mu is equal to 1, okay. Um, the qualitative nature of the phase line changes when mu equals 1. We say that a bifurcation occurs at mu equals 1, and it's called a bifurcation value. The graph of f1, yeah, okay, good. We get it. It's a parabola and with the minima at the axis. Okay, so the fact that the bifurcation occurs at the parameter value for which the equilibrium point is a node is no coincidence. In fact, this bifurcation scenario is quite common. The bifurcation diagram. An extremely helpful way to understand the qualitative behavior of solutions is through the bifurcation diagram. This diagram is a picture in the mu y plane. So, bifurcation diagram is a mu y plane plot of the phase lines near a bifurcation value. It highlights the changes that the phase lines undergo as the parameter passes through this value. To plot uh, the bifurcation diagram, we plot the parameter values along the horizontal axis for every mu value, not just integers. We draw the phase line corresponding to mu. We draw the phase line corresponding to mu on the vertical line through mu. Right. Okay. I mean, this is all obvious. Just reading it is. We think of the bifurcation diagram as a movie. As our eye scans the picture from left to right, we see the phase lines evolve through the bifurcation. Figure at 1.83 shows the bifurcation diagram. What did you do when I met you in the summer? Okay. So wait, if I do y is equal to 1 plus minus, can I do a plus minus? Okay. All right, cool. So that was like the simple first example. So this is the example is y squared f of y is equal to y squared minus 2y plus mu. Okay, now 1 to 3 equal bifurcation. Let's look at another one parameter family of differential equations. G of alpha of y is equal to y cubed minus alpha y is equal to y times y squared minus alpha. Okay, so immediately if alpha equals 0, right, so if we set this, so if we just try to, we set it to 0, so we get 0 equals y cubed minus alpha y. Then we get alpha y equals y cubed. Then we get alpha is equal to y squared. So whenever alpha equals y squared, we have an equilibrium. Equilibrium. School is prison. Yeah. Okay. Okay, so right. Okay, so we have 3 equilibria if alpha is greater than 0. But there's only one equilibrium point if alpha is less than or equal to 0. Therefore, a bifurcation occurs when alpha equals 0. To understand this bifurcation, we plot the bifurcation diagram. So 3 to 1, 1 to 3. If alpha is less than 0, then y squared minus alpha is always positive. Thus, g sub alpha of y has the same sign as y. Solutions tend to infinity if y 0 is greater than 0. Let's see, how long is this? Okay. Oops. We're always going to have this one, but this one is going to be a 2 to 0 type of thing. Okay, 11 is a good problem. This one's interesting. All right. Oh, and then the match 'em up ones. The match 'em up ones are fun. Oh, we've considered this model before. Ugh. Oh my god, dude. Um, Dude, polynomials are so cool. Polynomials are crazy, man. Sketch the graph of a function. Okay, so that's a category of problem is sketch something. You can totally have two semi-stable nodes next to each other. Um, this is two semi-stable nodes. All right. Is it possible to find a continuous Okay, so these are like the satisfaction problems of like, yeah, okay. That's pretty good. I haven't considered this model before. 19 is good. I don't know how to solve this one. Given the possibility of unexpected perturbations of the population not included in the model, what do you think will happen to the actual fish population if we allow? Okay. So we clearly have to do a lot. I mean, we definitely have to do these problems. It's amazing how much single variable differential equations get studied in this. Ooh, 21 is good. Dang, these are good problems. I don't know how to do that. Okay, so we looked at some of the problems. Now we can Alright, so we looked at this. What is this? Is this for no, it's not. Okay, bifurcations of equilibrium points. Throughout the rest of this section, we assume that all the one parameter families of differential equations that we consider depend smoothly on the parameter. That is, the partial derivatives of f mu y with respect to y and mu exist and are continuous. So changing mu a little changes the graph of f mu y only slightly. When bifurcations do not happen. The most important fact about bifurcations is that they usually do not happen. A small change in the parameter usually leads to only a small change in the behavior of the solutions. this is very reassuring. For example, suppose we have a one parameter family. And the differential equation has an equilibrium point. And then we have a sink. Okay, so y0 is a sink. We sketch the phase line and graph. Okay, here we go. So it's a sink. Now, if we change mu just a little bit, then the graph is still very close. So meaning it just changed a little bit. So the graph is strictly decreasing near y0. Wait, hold on. If we change mu just a little bit, then the graph is very close to the original graph. So the new graph is strictly decreasing near y0. Wait, I didn't get that. Anyways, so it's saying a sink. If y0 is a sink, then for all mu 1 sufficiently close also has a sink. Okay. All right, and a similar statement holds for y0 as a source. There are situations in which we can say for sure that no bifurcation occurs. These are the situations in which we can say for sure that no bifurcation occurs, at least not near y0. We see that bifurcations only occur only if the above conditions do not hold. What conditions? Determining bifurcation values. Consider one parameter family. All right, so if mu equals 0, then we get this as our differential equation, and we have two equilibrium points. And then they evaluated what would that be? That'd be, geez, that's actually more than I thought. So it's going to be y times 1 minus y times 1 minus y. So we'll do 1 minus 2y plus y squared times y. So it's actually of degree 3. I thought it was of degree 2. But anyways, the point is y minus 2y squared plus y cubed. And that is if you take the partial of that with respect to y, we're going to get 1 minus 4y plus 3y squared. And so they evaluated that point at 0, and they got 1. Okay, yeah. Great. So, we just verified that this is true. And so since the partial at the equilibria, so the slope as it hits the x-axis, as it being the differential equations, the dy dt, as dy dt hits the x-axis, or the y-axis here, I guess, its slope is 1, so it's going up. So that means that it's a source. Okay, so we have a source. Oh, God. Okay, so where were we? We were talking about. I mean, what is this section about? For mu slightly negative, the differential equation has two equilibrium points near y equals 1. Since f sub mu is decreasing at one of these and increasing on the other. One's a sink and one's a source. Patience, young Padawan. Patience. F sub mu decreasing, they're talking about the linearization around these two equilibria for which mu is less than 0. So there is a second bifurcation in this one parameter family. To see this, note what happens as mu decreases. There's a value of mu for which f mu y, again, has a tangency. Oh, that's a crazy plot. Yeah, that's a wild plot. So we can have, there's like a zone where there's 3. Oh, that's so cool. Wow, this plot is so fun. That's the plot, that's wild. All right, sustainability. When harvesting a natural resource, it is important to control the amount harvested so that the resource is not completely depleted. To accomplish this, we must study the particular species involved and pay close attention to the possible changes that may occur if the harvesting level is increased. Okay. Suppose we model the population of a particular species of fish with a logistic model. I like the logistic model. It's easy to understand and it has carrying capacity in it. Suppose that that fishing removes a certain constant number of fish per year or per season. Then a modification of the model that takes fishing into account is how does the population of fish vary as C is increased? This model has 3 parameters, K, N, and C. We are only concerned with what happens when C varies. Therefore, we think of K and N as fixed constants determined by the type of fish and their habitat. Our predictions involve the values of K and N. For example, if C equals 0, then we know Actually, hold on. Let's just take the normal. Logistic equation. So if we type in here. Oops. I don't know what I just did. Oh, but we're talking about solutions. What's up, Vamshi? All right, so we get okay. Is that true? Okay, well we know that it's going to be 0 at p equal 1. So what I'm trying to figure out is we're going to have okay, so we could just do this. Okay. So fishing is prohibitive. We expect the population to be close to p is equal to n. Yep. As c increases, the graph of yeah, okay. All right. As c increases, the graph of fc of p slides down. The points where it crosses the p-axis tend the points where it crosses the p-axis tend toward each other. What? The points. They're saying okay, yeah. In other words, the equilibrium points for the corresponding differential equations slide together. Yeah. We can compute them. Okay, so here we go. So let's say we have, kp 1 minus p over n minus c is equal to 0. And we want to solve. Okay, so kp minus kp squared over n. Wait. And then they multiply both sides by n, and they get k minus k p squared plus kpn minus cn is equal to 0. And then they, oh wow, okay. So then they use the quadratic formula to find I'm curious, when did the quadratic formula, when did it come out? Babylonian times, dude. Never heard of this guy before. That's cool. Pretty old. People have been studying this for so long. It's just beautiful, you know? It's just so beautiful. So as long as the thing is, all the subset of the examples that we've done, dude, I don't know any of this. What the hell? Wait, what is the statement of the what is the statement of the theorem? Hmm. All right, let's just get through this last bit. Actually, there's a lot more. Maybe I'll pick it up. Oh wait, actually, there's not more. There's not a lot more. I'll be right back. Okay, come on. There's like one page left of notes to read. All right, so they apply the quadratic formula to this logistic model with harvesting. Okay, so let's just take the stuff inside the square root. N squared over 4 is equal to C n over k, or is minus and is equal to 0. So so yeah, if we get n squared k, or we get nk over 4 is equal to c. And so this, so basically if the under the square root is n squared over 4 minus Cn over K. So if C, so when C is equal to Nk over 4, Kn over 4, then there's exactly one solution. So that's going to be the node case or something like that when you're sort of on the boundary of whether there's 0 equilibrium points or there's 2, and you have 1. And so if C is greater than, then no solutions. No real solutions. For these values of C, negative populations don't make any sense, so we say that the species has become extinct. With this information, we can sketch the bifurcation diagram for this system. Okay. The graph of FCP is tangent to the p-axis. Okay, so that's that line. Right, when C is 0, we have 2. We have 2. This doesn't actually say... Or I guess that is when P is 0. Yeah, okay. All right, let's just read it. Okay, if C is equal to 0, the population tends to the sink at P equal to N. Then if there's a relatively small amount of fishing, the fish population is still close to P is equal to N. That is, if C is slightly positive, the sink for C equal to 0 at P equal to N moves slightly to a smaller value. For somewhat larger values of C, the value of the sink continues to decrease and the fish population adjusts to stay close to this sink. We observe a gradual decrease in the fish population. When C is close to Kn over 4, the fish population is close to the sink for the corresponding differential equation, which is close to N over 2. If C increases just a little more so that C is greater, then the corresponding differential equation has no equilibrium points and all solutions decrease. If C is slightly larger, it's slightly negative, so the population decreases slowly. As P decreases, FC of P becomes more negative and the rate accelerates. The population reaches 0 and the fish go extinct. So the number of fish removed by fishing... So as the number of fish removed by fishing increases gradually, we initially expect a gradual decline in the fish population. This decline continues until the fishing parameter reaches the bifurcation value. At this point, if we allow even slightly more fishing, the fish population decreases slowly at first and then collapses. And the fish become extinct in the area. This is a pretty frightening scenario. The fact that a little fishing causes only a small population decline over the long term does not necessarily imply that a little more fishing only causes a little more population decline. Right. This is the whole point of all of this. Nonlinearity, bifurcations, things are not always, like this. Once the bifurcation value is past the population, it's over. This model is a very simple one, and it shouldn't be taken too seriously. The lesson to be learned is that if this sort of behavior can be observed in simple models, we would expect that the same and even more surprising behavior occurs in more complicated models and in the actual populations. To properly manage resources, we need to have accurate models to be aware of possible bifurcations. That's a good note to end on. I'm not going to do the exercise. We'll do the exercise tomorrow. Okay.